James Webb Telescope saw first object beyond dark ages, and it is forcing us to rethink everything we thought we knew about the dawn of time. For decades, astronomers believed the early universe was a dark, empty void, slowly cooling before the first stars could ignite. But as the golden mirrors of the Webb telescope peered into that ancient silence, they didn't find the faint flickers of infant suns. They found something else entirely. Something that by every model and every prediction we had should not have been there. What the telescope picked up were tiny red dots, barely visible smudges of light that had traveled for more than 13 billion years just to reach us. And when scientists began pulling apart that light, stretching it and studying its fingerprint, the answers that came back left some of the brightest minds in astrophysics genuinely confused. Those faint red dots were not the delicate beginnings of star formation. They were fully formed galaxies, massive ones, some as large as our own Milky Way, and they existed at a time when, according to everything we understood about how the universe works, nothing that large should have had the chance to form yet. But before we get to what that means and why it might change everything we think we know about reality itself, we need to go back to the very beginning, because this story does not start with the Webb telescope. It does not even start with galaxies. It starts with silence. A deep, total cosmic silence that lasted for hundreds of millions of years. After the Big Bang about 13.8 billion years ago, the universe was unimaginably hot. Everything that would eventually become every star, every planet, every molecule in your body existed as a screaming soup of particles and energy. Protons and electrons slammed into each other constantly, and photons, the particles of light, could not travel more than a tiny distance before bouncing off something else. The universe in those earliest moments was not dark at all. It was blindingly bright, but it was also completely opaque. Light could not escape. It was trapped in the chaos. Then, roughly 380,000 years after the Big Bang, something changed. The universe cooled down just enough for protons and electrons to stop crashing into each other, and instead come together to form the first neutral hydrogen atoms. This was a quiet but enormous shift. Suddenly light was free. Photons could travel without being scattered. That ancient light released in that moment is still detectable today. We call it the cosmic microwave background, and it fills every direction of the sky. It is the oldest light we can see. But here is the thing. After that moment, after those atoms formed, and the light was set free, nothing else happened. Not for a very long time. The universe entered a period that scientists call the cosmic dark ages. No stars, no galaxies, no structure of any kind. Just a vast cooling ocean of hydrogen and helium gas slowly drifting in the dark. And when we say dark, we mean truly dark. There was nothing to produce visible light. The cosmic microwave background had stretched and faded as the universe expanded, shifting from a brilliant glow to invisible microwave radiation. The universe, for all practical purposes, had gone blind. This period lasted somewhere between 100 million and several hundred million years. In human terms, that might seem like an impossibly long stretch, but in cosmic terms, it was actually remarkably brief. The universe was just getting started. During those dark ages, something was happening that could not be seen. Gravity was pulling. Slowly, very slowly, the gas that filled the universe began to clump. Dark matter, that invisible substance we still do not fully understand, had already begun forming the scaffolding of what would become the cosmic web. These enormous invisible filaments of dark matter stretched across the universe, and along those filaments regular matter, the hydrogen and helium gas, started to gather. The denser pockets of gas grew denser still. Gravity is patient. It does not rush, but it also never stops. And in certain regions where just a little more matter had collected, then average gravity began to win its long, slow battle against the expansion of space. And then somewhere in that endless night, the first light appeared. We do not know exactly when it happened. We do not know exactly where. But at some point, a cloud of hydrogen gas had compressed so much under its own gravity that the temperature and pressure at its center reached a point of no return. Nuclear fusion ignited. Hydrogen atoms were slammed together hard enough to fuse into helium, releasing energy in the process. A star was born. Not a star like our sun. Nothing like it. These first stars, which scientists call population 3 stars, were monsters. Theoretical models suggest they could have been hundreds of times more massive than the sun. Some models push that number even higher into the thousands. They would have been intensely hot with surface temperatures around 90,000 degrees, roughly 10 times hotter than our sun. They would have glowed with a fierce blue-white light, pouring out ultraviolet radiation so intense that it would begin to tear apart the very atoms around them. And they would have burned fast. A star like our sun will last for about 10 billion years. These early giants probably lasted only a few million, maybe less. They lived fast, they burned bright, and then they exploded. When they died, they went out in spectacular fashion. As supernovae so powerful, they would have briefly outshone entire galaxies. But those explosions were not just endings, they were beginnings. Because when those first stars exploded, they flung newly forged elements out into the universe. Carbon, oxygen, nitrogen, iron. Elements that had never existed before, cooked up in the cores of those titanic stars and scattered into space by their deaths. These elements would eventually become the building blocks of planets, of oceans of living things. Something about this whole process still does not add up, though. And that is where the James Webb Space Telescope enters the story. For years, scientists had a relatively comfortable picture of how things should have gone after the Dark Ages ended. The first stars lit up. They lived short, violent lives. Their explosions scattered heavy elements into the surrounding gas. That enriched gas then collapsed into new clouds, forming second-generation stars and eventually the first small galaxies. These early galaxies were expected to be tiny, faint, irregular clumps of stars. Nothing impressive, just the humble seeds of what would eventually grow into the grand spirals and giant ellipticals we see in the universe today. The growth was supposed to be gradual. Small galaxies would merge with other small galaxies over hundreds of millions of years, slowly building up mass. It was a story of patience and accumulation. A universe that took its time assembling itself piece by piece like a puzzle being put together over billions of years. The Webb telescope was built in large part to observe this process. It was designed to look further back in time than any telescope before it, using its enormous golden mirror and its suite of infrared instruments to detect the faintest, most distant light in the universe, light that had been traveling since the cosmos was in its infancy, light that had been stretched by the expansion of the universe from visible wavelengths into the infrared, invisible to our eyes, but not to Webb. And what Webb found almost immediately was that the comfortable picture was wrong. In the first year of observations, teams of astronomers using Webb began reporting the detection of galaxies at staggering distances. Not just any galaxies. These were big, bright, and structurally mature. They contained billions of stars. Some showed signs of organized structure, spiral arms, dense cores, things that were not supposed to exist so early in cosmic history. One galaxy in particular, designated JWST Z140, became a kind of symbol for the confusion. Detected by the JD Survey Team, which stands for the JWST Advanced Deep Extragalactic Survey, this galaxy was confirmed to exist just 290 million years after the Big Bang. Its light had been stretched by a factor of roughly 15, meaning it was extraordinarily far away and extraordinarily old. But it was also over 1,600 light-years across, and its light appeared to come primarily from young stars, not from a black hole at its center. That matters because when a galaxy appears very bright but very distant, one possible explanation is that a supermassive black hole is doing most of the heavy lifting. Gas falling into a black hole heats up and radiates energy so intensely that it can outshine the entire rest of the galaxy. But JWST did not seem to have that excuse. Its brightness appeared to come from actual star formation, which meant it genuinely contained a huge number of stars already in place. The team that found it described the discovery as completely unanticipated, and they noted that the telescope could have detected this galaxy even if it had been 10 times fainter, meaning there were probably many more like it out there, possibly at even earlier times. This was not an isolated finding. Across multiple surveys, Webb kept turning up galaxies that were too big, too bright, and too well formed for the age of the universe at the time they existed. Some researchers called them impossible galaxies, though that phrase is a bit misleading. They are not impossible in the sense that they cannot exist. They clearly do. They are impossible in the sense that our best models did not predict them. And that distinction matters a great deal. When a telescope sees something unexpected, there are really only a few options. Either the observations are wrong, the interpretations are wrong, or the models are wrong. In this case, the observations have been checked and rechecked. The instruments on Webb are working beautifully. The data is solid, so the question becomes one of interpretation and modeling. Some scientists suggested that what looked like massive galaxies might actually be something else. Perhaps supermassive black holes at the centers of these objects were making them appear brighter and more massive than they really were. This turned out to be partly true in some cases. A class of objects dubbed little red dots, small compact sources with a reddish appearance, do seem to harbor actively feeding black holes that inflate their apparent brightness. A study led by Catherine Chorowski at the University of Texas at Austin showed that when you remove these little red dots from the analysis, the remaining galaxies are not massive enough to truly break the standard model of cosmology. The panic, in other words, was partly a false alarm, but only partly. Because even after accounting for the little red dots, there are still roughly twice as many massive galaxies in Webb's data as the standard model predicts. Not enough to shatter our understanding of the universe, but definitely enough to suggest that something about how the earliest galaxies formed was different from what we assumed. One leading explanation involves a concept called bursty star formation. In the modern universe, star formation tends to be a slow, steady process. Gas collapses, heats up, pushes back against gravity, and eventually forms stars at a moderate pace. But simulations suggest that in the early universe, when galaxies were smaller and the surrounding environment was much denser, the process might have been very different. Instead of forming stars steadily, these early galaxies might have gone through intense bursts of star formation, followed by quiet periods, followed by more bursts. During the bright bursts, the galaxy would look much more luminous than its actual total mass would suggest. And because the most massive stars, the ones that shine the brightest, are also the ones that die the fastest, the galaxy's brightness would fluctuate wildly over time. If we happened to catch these galaxies during one of their bright bursts, they would look far more massive and impressive than they really were. This is a clever explanation, and the simulations that support it are promising. But it does not answer every question, because there is another puzzle here, one that runs even deeper than the question of how many galaxies exist, and it has to do with what is inside them. When the Webb telescope peers into the spectrum of a distant galaxy, it does more than just measure brightness. It reads the chemical fingerprint of the light. Every element in the universe absorbs and emits light at specific wavelengths, like a barcode that is unique to that element. By spreading out the light from a distant galaxy into its component wavelengths, scientists can figure out what elements are present and in what quantities. In galaxies close to us in the modern universe, this chemical fingerprint is rich and complex. You find hydrogen, helium, carbon, nitrogen, oxygen, iron, and dozens of other elements. That is because billions of years of stellar life cycles have enriched the gas over and over again. Stars form, they burn, they explode, they scatter heavy elements, and the next generation of stars incorporates those elements into its own composition. Each cycle adds more complexity to the mix, but in the very early universe this process had barely started. The first stars, those population 3 giants we talked about, formed from gas that was almost entirely hydrogen and helium, with just a trace of lithium. No carbon, no oxygen, no iron. Nothing heavier than those 3 lightest elements. When those first stars exploded, they would have produced the first batches of heavier elements. But it should have taken time for those elements to spread through the surrounding gas and get incorporated into new stars and galaxies. So when Webb looked at some of the most distant galaxies ever observed, scientists expected to see very simple chemical signatures. Lots of hydrogen, some helium, maybe trace amounts of a few heavier elements. What they found instead was far more complicated than that. Some of these ancient galaxies showed surprisingly high levels of certain elements. In particular, several galaxies displayed an unusual ratio of nitrogen to oxygen that could not be explained by normal stellar processes. The galaxy GS 3073, observed just over 1 billion years after the Big Bang, had a nitrogen to oxygen ratio that was far higher than anything ordinary stars could produce. This is a very specific and very telling clue. A team of researchers realized that the only way to produce such an extreme nitrogen signature was through the nuclear burning processes that would occur inside truly supermassive stars between 1,000 and 10,000 times the mass of the Sun. These are the kinds of stars that only population 3 theory predicts. In those enormous stellar furnaces, carbon, produced by helium fusion, leaks into hydrogen-rich layers where interactions between carbon and hydrogen produce large amounts of nitrogen. When such a star eventually explodes, it scatters that nitrogen-rich material into the surrounding galaxy. The chemical fingerprint in GS 3073 matched this prediction almost perfectly. It was, according to the research team, the first observational evidence that these monster stars had actually existed. Not indirect hints, not theoretical predictions. Actual chemical traces left behind in a galaxy that formed when the universe was barely starting to wake up from its dark ages. And GS 3073 was not alone. Another galaxy called LAP1b, located more than 13 billion light-years away and magnified by the gravitational lensing of a massive galaxy cluster between us, and it showed spectral signatures consistent with population 3 stars as well. The gas surrounding LAP1b contained helium, but virtually no heavier elements. Exactly what you would expect if the first generation of stars had only recently formed and died there. The detection of LAP1b was particularly significant because it met 3 theoretical conditions that had been laid out in advance as tests for identifying real population 3 stars. The system formed in a low metallicity environment, meaning very few heavy elements were present. The temperature was right for star formation, and the mass distribution of the stars matched mathematical predictions for what the initial mass function of population 3 stars should look like. But here is the puzzle that makes this even more interesting. If these truly are the chemical fingerprints of the first stars, then the timing raises uncomfortable questions, because the galaxies where these signatures appear already contain organized structure. They already have some degree of complexity, and they exist at times when the simplest models suggest the universe should still have been in the very early stages of building anything at all. It is as though we expected to find scattered bricks at a construction site and instead found a half-built house. The materials are right, the signatures make sense, but the progress is too far along for the time available. And this problem only gets worse when we start looking at what else Webb has found hiding in the hearts of these early galaxies. Supermassive black holes, enormous ones, far more of them and far earlier than anyone had predicted. In the modern universe, virtually every large galaxy has a supermassive black hole sitting at its center. Our own Milky Way has one called Sagittarius A star, with a mass of about 4 million times that of the Sun. That sounds enormous, but compared to the total mass of the Milky Way, it is actually quite small. In nearby galaxies, the ratio of the black hole mass to the total stellar mass is typically about 1 to 1,000. The galaxy outweighs its black hole by a factor of roughly 1,000 to 1. This ratio is remarkably consistent across different types of nearby galaxies. It has led astronomers to believe that galaxies and their central black holes grow together in a kind of partnership, each one influencing the other's development over billions of years. But when Webb looked at the earliest galaxies, this partnership appeared to be wildly out of balance. The black holes were too big, way too big. In some cases, the black hole at the center of a young galaxy was not 1,000th of the galaxy's stellar mass. It was 1/10, or 1 to 1. In at least one case, the black hole appeared to outweigh the combined mass of all the stars in its host galaxy. A study led by Fabio Pacucci at the Harvard and Smithsonian Center for Astrophysics examined 21 supermassive black holes detected by Webb in the early universe. Every single one of them was overmassive relative to the galaxies they lived in. The black holes were between 10 and 100 times heavier than the established relationship would predict. That is not a minor discrepancy. That is a fundamental challenge to our understanding of how both galaxies and black holes form. The traditional picture of how supermassive black holes grow starts small. A massive star explodes as a supernova and leaves behind a stellar mass black hole maybe 10 to 100 times the mass of the Sun. Over time, these black holes merge with each other and swallow surrounding gas, gradually building up their mass. Given enough time, perhaps several billion years, they can grow to millions or billions of solar masses. But given enough time is exactly the problem. In the earliest galaxies that Webb has observed, which exist within the first billion years after the Big Bang, there simply has not been enough time for this gradual build-up to work. The math does not add up. You cannot start with a small seed and grow it to 1 billion solar masses in less than 1 billion years through normal feeding processes. There are physical limits on how fast a black hole can consume matter, known as the Eddington limit, which is set by the balance between the inward pull of gravity and the outward push of radiation pressure from the infalling material. And yet, one black hole observed by Webb, designated Elid 568, and seen about 1.5 billion years after the Big Bang, appeared to be feeding at more than 40 times its Eddington limit. 40 times faster than physics says should be possible through steady accretion. The researchers studying it found enormous outflows of gas surrounding the black hole, suggesting a single colossal feeding frenzy that may have given the black hole most of its observed mass in one event. Something about the early universe made it possible for black holes to grow at rates that border on the absurd, and scientists are still trying to figure out what that something was. One possibility is that the black holes did not start small at all. Instead of growing from the remnants of dead stars, perhaps some black holes in the early universe formed through a completely different process called direct collapse. In this scenario, a massive cloud of primordial gas, one that had never formed stars, collapses directly into a black hole without going through the star stage at all. This could produce a black hole weighing tens of thousands or even hundreds of thousands of times the mass of the Sun, right from the start, a heavy seed rather than a light one. There is now mounting evidence from Webb that this might actually be what happened. The MIT team that studied 6 ancient quasars with Webb found that the light from the stars around these black holes was surprisingly faint compared to the black hole's own radiation. This is consistent with a scenario in which the black hole got a head start, forming from a heavy seed and growing rapidly before the surrounding galaxy had time to build up its own stellar mass. Another even more exotic possibility has recently gained attention. What if some black holes did not form from gas at all? What if they formed from dark matter? This idea sounds radical, but it follows from certain theoretical models of how dark matter behaves. In the standard model, dark matter particles interact with each other only through gravity, but some theories propose a property called self-interaction, where dark matter particles can collide with and scatter off each other. If this self-interaction is strong enough, dark matter could pile up in the centers of early galaxies, forming incredibly dense cores that eventually collapse under their own weight into black holes. A team at the University of California, Santa Cruz explored this idea and found that it could explain how supermassive black holes formed early enough and large enough to match what Webb is seeing. Their model successfully reproduced the properties of 3 well-studied early quasars without requiring any exotic astrophysical processes, just a tweak to the nature of dark matter itself. If true, this would not only solve the mystery of early supermassive black holes, it would also tell us something profound about the very nature of dark matter, a substance that makes up about 27% of the total mass and energy of the universe, but that we have never directly detected. But we are getting ahead of ourselves, because the mystery of the black holes is connected to an even larger puzzle, one that involves the entire history of how the universe went from dark and foggy to clear and transparent. And it is a puzzle that Webb has made significantly more confusing. It is called the Epoch of reionization, and it is one of the most important and least understood chapters in cosmic history. Remember those first neutral hydrogen atoms that formed 380,000 years after the Big Bang? The ones that allowed light to travel freely for the first time. Well, those atoms did not stay neutral forever. Something happened to them. At some point, the ultraviolet light pouring out of the first stars and galaxies began to tear those neutral atoms apart again. The photons were energetic enough to knock the electrons off the hydrogen atoms, splitting them back into their component parts. This process, called ionization, did not happen all at once. It started in small bubbles around the brightest galaxies and gradually spread outward as more and more sources of ultraviolet light appeared. Imagine a dark fog filling the entire universe. Now imagine that each new galaxy that forms is like a lamp being turned on inside that fog. At first, each lamp only clears a small pocket of fog around itself. But as more lamps appear and grow brighter, the cleared pockets expand and start to merge. Eventually, the fog is gone entirely, and the universe becomes transparent to ultraviolet light. This process, known as reionization, is believed to have started a few 100 million years after the Big Bang and finished roughly 1 billion years later. It was a defining transition in cosmic history, the moment the universe went from being a dark, foggy place to the clear, transparent one we observe today. Before Webb scientists had some general idea of how this process worked, based on indirect evidence from the cosmic microwave background and from observations of distant quasars, whose light is partially absorbed by any remaining neutral hydrogen along the line of sight. The picture was that reionization was mainly driven by small faint galaxies that produced lots of ultraviolet light. These tiny galaxies were expected to be the workhorses of the process, gradually chipping away at the fog over several 100 million years. But Webb has thrown a wrench into this picture. The problem, in short, is that Webb has found far too many galaxies in the early universe, and they appear to be producing far more ultraviolet light than anyone expected. If you add up all the ultraviolet output from all the galaxies Webb has detected in the first billion years, you get a number that is much, much higher than what the standard models predicted. And that creates what some scientists are now calling a photon budget crisis. There are simply too many photons, too much light. If all of these galaxies were pumping out ultraviolet radiation at the rates that Webb's data suggests, then reionization should have happened much faster than it actually did. It should have started earlier and ended sooner. But the cosmic microwave background and the quasar absorption data both tell us that reionization did not end until the universe was roughly 1 billion years old. Those measurements have not changed. They are among the most robust in all of cosmology. So we have a contradiction. The galaxies say reionization should have been quick. The background radiation and quasar data say it was slow. Both sets of data appear to be correct, and yet they do not agree. Something has to give. One possibility is that we are overestimating how much ultraviolet light actually escaped from these early galaxies. In the modern universe, most of the ultraviolet light produced by stars gets absorbed by gas and dust within the galaxy itself. Only a small fraction escapes into intergalactic space. If something similar happened in the early universe, if most of the ultraviolet light was trapped inside the galaxies, then the photon budget problem might go away. But the early universe had very little dust. Dust is made of heavy elements which are made in stars. In the very earliest galaxies, there had not been enough time for significant amounts of dust to accumulate. So the escape fraction should have been higher, not lower, than it is today. Another possibility involves the neutral hydrogen itself. Perhaps the gas between galaxies was not just being ionized by starlight, but was also recombining with protons and electrons coming back together to form neutral atoms again. If recombination was happening fast enough, it could slow down the overall pace of reionization, even if the photon production rate was very high. This is an active area of research, and no one has a definitive answer yet. But the fact that Webb has created this tension, this mismatch between what the galaxies are doing and what the universe as a whole seems to be telling us, is one of the most fascinating developments in modern cosmology. It suggests that something about the early universe is fundamentally different from what we assumed. Not wrong in a catastrophic, throw everything out way, but different in a way that requires us to rethink some of our basic assumptions about how the first light sources interacted with the gas around them. And speaking of rethinking our assumptions, there is another crisis brewing in cosmology right now that the Webb telescope has made worse, not better. It has nothing to do with galaxies or black holes or the first stars. It has to do with how fast the universe itself is expanding. This is the Hubble tension, and it is, according to some scientists, the biggest crisis in astronomy today. The story starts with a number. It is called the Hubble constant, named after Edwin Hubble, who in the 1920s discovered that the universe is expanding. The Hubble constant tells us how fast that expansion is happening right now. Measuring it precisely has been one of the great quests of modern cosmology, because the expansion rate is tied to almost everything else. It tells us the age of the universe, the size of the observable universe, and the ultimate fate of everything in it. There are two main ways to measure the Hubble constant. The first starts with the cosmic microwave background, that ancient light from 380,000 years after the Big Bang. By studying the tiny temperature fluctuations in the CMB and running them through the standard model of cosmology, scientists can predict what the expansion rate should be today. This method gives a value of about 67.4 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. So what this number means is that for every 3.26 million light years of distance between two objects, the space between them is growing by 67.4 kilometers every second. The second method measures the expansion rate directly by looking at things in our local neighborhood of the universe. Astronomers use a technique called the cosmic distance ladder, which involves measuring the distances to progressively more distant objects using a chain of overlapping methods. You start with nearby stars whose distances can be measured geometrically. Then you use a special type of pulsating star called a Cepheid variable, whose brightness is related to its pulsation period, to measure distances to more distant galaxies. Then you use type Ia supernovae, which all explode with roughly the same brightness to reach even further. This local method gives a value of about 73 kilometers per second per megaparsec. The difference between 67 and 73 might not sound like much, but in the world of precision cosmology, it is enormous. The statistical significance of the disagreement has reached 5 sigma, which in science means there is less than a 1 in 3.5 million chance that this difference is just a random fluke. For years, many astronomers hoped the problem would go away. Maybe there was a subtle error in the Cepheid measurements. Maybe dust or crowding in distant galaxies was throwing off the brightness estimates. The Webb telescope was supposed to help settle this by providing sharper, cleaner images of those same Cepheid stars. It did not settle anything. In fact, it made things worse. When the Webb telescope observed the same Cepheid stars that had been measured by Hubble, the results matched almost perfectly. The local expansion rate measurement held up. There was no systematic error from dust, no problem with crowding. The number was real. And then, in January 2025, a team led by Daniel Skolnick at Duke University measured the expansion rate using a different approach, looking at the nearby Coma galaxy cluster and calibrating the distance ladder from there. Their result was even higher, 76.5 kilometers per second per megaparsec, even further from the prediction of the standard model. Skolnick declared that the Hubble tension was no longer just a tension. It was now a crisis. What does this mean? It means that the universe in its early days, as described by the cosmic microwave background and the standard model, predicts a certain expansion rate today, and the universe in its current state, as measured directly, is expanding measurably faster than that prediction. Either there is a subtle error somewhere that nobody has been able to find despite years of searching, or the standard model of cosmology, the framework that has successfully explained almost everything we observe about the universe for decades, is missing something. that missing something could be a new form of energy. Some theorists have proposed an idea called early dark energy, a brief burst of extra energy that pushed the universe to expand faster during its first few 100,000 years. If such a push happened, it would change the predicted expansion rate and potentially bring the two measurements into agreement. Others have proposed modifications to the nature of dark matter or new particles that existed only in the early universe, or changes to the way gravity works at very large scales. None of these ideas has been confirmed. None has emerged as a clear favorite. And the tension remains. What makes this relevant to the story of the Webb telescope and the first objects beyond the Dark Ages is that all of these puzzles may be connected. The same standard model that fails to predict the correct expansion rate also failed to predict the abundance and maturity of early galaxies. The same early universe that seems to have produced structure faster than expected also seems to have been expanding at a rate that does not quite match its own initial conditions. It is possible that all of these problems have the same root cause, and finding that cause would represent one of the most significant breakthroughs in the history of physics. But let us return to the telescope itself for a moment, because the Webb telescope is not just an instrument. It is a kind of time machine, and understanding how it works helps us appreciate just how remarkable these discoveries are. The James Webb Space Telescope orbits the Sun at a point called the second Lagrange point, or L2, about 1.5 million kilometers from Earth. At this location, the gravitational pulls of the Earth and the Sun combine in just the right way to allow the telescope to orbit the Sun in sync, with the Earth always staying on the far side from the Sun. This is important because the Webb telescope is designed to see infrared light, and infrared light is basically heat radiation. Everything that is warm emits infrared light. Your body emits it. The Earth emits it. Even the telescope itself emits it. To detect the incredibly faint infrared signals from the most distant galaxies in the universe, the telescope needs to be extraordinarily cold. Its instruments operate at temperatures around 40 Kelvin, which is about minus 233 degrees Celsius. One of its instruments, the mid-infrared instrument, or MIRI, needs to be cooled to just 7 Kelvin colder than the surface of Pluto. To achieve these temperatures, the telescope has a sun shield the size of a tennis court, 5 layers of a special material called kapton, each thinner than a human hair block, the light and heat of the Sun, the Earth, and the Moon. On the hot side of the sun shield, temperatures can reach 85 degrees Celsius. On the cold side, they drop to below minus 230. The difference between the two sides is more than 300 degrees. The telescope's primary mirror is 6.5 meters across, made up of 18 hexagonal segments coated in a thin layer of gold. Gold is used because it is an excellent reflector of infrared light. Each mirror segment can be individually adjusted to a precision of about 1/10,000th the width of a human hair. The entire mirror assembly had to be folded up to fit inside the Ariane 5 rocket that launched it, and it unfolded itself in space over the course of several weeks after launch. The fact that this telescope works at all is a kind of miracle of engineering. There were 344 single points of failure during the deployment process, 344 things that had to go exactly right, or the entire mission would have been lost. Every single one of them worked, and because it worked, we can now see things that were literally invisible before. We can look back to within a few 100 million years of the Big Bang and detect the faint infrared glow of the first structures that formed in the universe. We can split that light into spectra and read the chemical fingerprints of the earliest stars. We can measure the masses and sizes of galaxies that existed when the cosmos was less than 5% of its current age. No other telescope can do this. The Hubble Space Telescope, which revolutionized astronomy in its own right, observes primarily in visible and near-infrared light. It can see galaxies out to about 1 billion years after the Big Bang, but the most distant ones are at the very edge of its capabilities, and it cannot see their details clearly. Webb picks up where Hubble leaves off, pushing into the infrared wavelengths where the most distant galaxies shine. And it is in those infrared wavelengths that the most surprising discoveries have been made. Let us talk about one more galaxy, because it illustrates something important about how discoveries happen in science. This galaxy has the rather unwieldy name JWST Z31, and it was found as part of the same JWST survey that detected the record-breaking JWST Z13 we discussed earlier. JWST Z13 exists at a time just 330 million years after the Big Bang. It is one of the most distant galaxies ever confirmed. But what makes it truly unusual is not just its distance, it is what its light is doing. When scientists studied the spectrum of this galaxy, they found something that, according to our current understanding, should not have been there. They detected a signature called Lyman alpha emission, which is a specific wavelength of ultraviolet light produced by hydrogen atoms. Lyman alpha emission is common in nearby galaxies, but at the distance and time period of JWST Z13 it should have been completely absorbed by the thick fog of neutral hydrogen that surrounded everything in the early universe. During the epoch of reionization, that fog of neutral hydrogen was supposed to be almost impenetrable to Lyman alpha light. It would soak it up like a sponge. For a galaxy this old and this distant to be showing clear Lyman alpha emission, it would need to have already carved out a significant bubble of ionized gas around itself, a clear pocket in the fog, large enough for the light to escape. The team estimated that this bubble would need to extend at least 650,000 light-years from the galaxy. That is a lot of clearing for such a young galaxy to have achieved in such a short time. One possible explanation is that the galaxy contains an active black hole at its center, which could produce intense radiation that helps ionize the surrounding gas. Another is that the galaxy is exceptionally efficient at producing ultraviolet light. But neither explanation is fully satisfying, and the researchers acknowledge that this galaxy challenges our established understanding of how the early universe transitioned from dark to light. As one team member put it, it is as though we expected to find thick fog everywhere and instead found a beam of light piercing through where no beam should have been. This kind of discovery is what makes the Webb telescope so transformative. It is not just finding things that are far away. It is finding things that force us to question what we thought we knew. Every new observation seems to push the boundaries of the possible a little further. And that brings us to one of the most profound questions that these discoveries raise. A question that goes beyond astronomy, beyond physics, into territory that borders on philosophy itself. What kind of universe are we living in? The standard model of cosmology called lambda CDM has been extraordinarily successful. Lambda refers to dark energy, the mysterious force that is accelerating the expansion of the universe. CDM stands for cold dark matter, the invisible substance that provides the gravitational scaffolding for galaxies. Together with ordinary matter, these ingredients make up the recipe for the universe. Dark energy accounts for about 68%. Dark matter accounts for about 27%. Everything else, all the stars, planets, gas, and dust that we can actually see, makes up about 5%. This model explains an enormous range of observations. It explains the cosmic microwave background. It explains the large-scale distribution of galaxies. It explains the expansion history of the universe. It explains the abundance of light elements produced in the Big Bang. It has passed test after test for more than 2 decades, but it does not explain everything. It does not explain what dark matter actually is. It does not explain what dark energy actually is. It does not explain why the Hubble constant measurements disagree. And now, thanks to Webb, it does not quite explain what happened in the first billion years of cosmic history. That does not mean the model is wrong in some catastrophic way. Science does not usually work like that. More often successful, models are found to be incomplete rather than incorrect. Newton's gravity worked beautifully for centuries before Einstein showed that it was a special case of a more general theory. Maxwell's equations of electromagnetism were perfectly accurate, but turned out to be part of a larger framework that included quantum mechanics. Lambda CDM may be heading for a similar fate. Not overthrown but extended, expanded to include new physics that we have not yet discovered. What might that new physics look like? That is where things get speculative but also deeply exciting. One possibility, as we mentioned, is early dark energy, a brief period of accelerated expansion in the young universe, different from the dark energy that drives acceleration today. This could change the predicted expansion rate and potentially explain why the universe seems to have gotten a head start on building structure. Another possibility involves the nature of dark matter itself. If dark matter particles can interact with each other in ways beyond just gravity, as the ultra-self-interacting dark matter model proposes, that could change how matter clumped together in the early universe. Stronger clumping would mean faster formation of galaxies and black holes, which is exactly what Webb is observing. A third possibility is even more radical. Some theorists have proposed that the age of the universe might be different from what we think. The standard model gives an age of 13.8 billion years based on the cosmic microwave background and the assumption that lambda CDM is correct. But if the model is wrong in some subtle way, the universe could be older than we think. An older universe would have had more time for galaxies and black holes to form, which would ease some of the tension. This is not a popular idea among mainstream cosmologists, but it is not impossible either. And it is the kind of radical rethinking that the Webb data might eventually force us to consider. There is also the question of whether the very first moments of the universe, the period of cosmic inflation that is believed to have occurred in the first fraction of a second, after the Big Bang, might have been different from what we assume. Inflation is the theory that the universe underwent an incredibly rapid expansion in its earliest moments, growing from smaller than an atom to larger than the observable universe in a tiny fraction of a second. This expansion smoothed out the universe and set the initial conditions from which everything else grew. But the details of inflation are poorly understood. Different models of inflation make different predictions about the distribution of matter in the early universe. If the initial conditions were slightly different from what we have assumed, that could change the predicted timeline for structure formation. Maybe gravity had more to work with than we thought. Maybe the seeds of the first galaxies were larger and denser than the standard models predict. Webb cannot directly test inflation. The light from that era has been stretched far beyond what any telescope can detect. But by studying what happened in the first few 100 million years after the Big Bang, Webb is placing tighter and tighter constraints on what those initial conditions must have been. And those constraints in turn tell us something about the very first instant of creation. It is remarkable when you think about it. A telescope floating in the cold of space 1.5 million kilometers from Earth, studying photons that have been traveling for more than 13 billion years, and in doing so, teaching us about events that happened in the first fraction of a second after the universe came into existence. That is the power of light. It carries information across unimaginable distances and unfathomable spans of time. And every photon that strikes the golden mirror of the Webb telescope is a messenger from the past carrying a story that has waited billions of years to be heard. Let us now turn to one of the most fascinating objects that Webb has revealed. Not a galaxy exactly, not a star, something stranger, something that appears to have two completely different identities depending on how you look at it. It is called Virgil, and it is one of the most puzzling objects in the early universe. Virgil is a galaxy that existed about 800 million years after the Big Bang. When scientists first observed it using Webb's near-infrared camera, it looked like a perfectly ordinary young galaxy, just another collection of stars quietly forming in the early cosmos. Nothing remarkable about it at all. But when they switched to Webb's mid-infrared instrument MIRI, something completely different appeared. At infrared wavelengths, Virgil transformed from a quiet, unremarkable galaxy into something much more dramatic. Hidden behind the optical and ultraviolet light of its young stars was a supermassive black hole shrouded in dust, actively consuming enormous amounts of material. The rate at which it was devouring gas far exceeded what astronomers would expect for a galaxy of its size and age. In visible and ultraviolet light, Virgil showed its good side, a typical young galaxy going about its business. But in the infrared, it revealed its true nature, a cosmic beast feeding in the shadows. This discovery highlighted something important that astronomers are still coming to terms with. The early universe may contain many more active black holes than we thought, and some of them might be completely invisible in the wavelengths that earlier telescopes could detect. Without MIRI, Virgil would have been classified as an entirely ordinary star-forming galaxy. Its hidden monster would have gone unnoticed. How many other galaxies in the early universe are hiding similar secrets? How many of those faint red dots in Webb's deep field images are actually dual-natured objects like Virgil appearing innocent in one light and ferocious in another? This is the kind of question that could take years to answer, but it points to a larger truth about what we are learning from the Webb telescope. The early universe was not the simple, quiet place we imagined. It was wild, it was turbulent, it was full of surprises. Recent work using Webb's near-infrared camera in a special observing mode called GRISM spectroscopy has confirmed this picture on a much larger scale. A team of researchers studied an entire population of galaxies between 400 and 600 million years after the Big Bang and found that most of them were chaotic and messy. Gas was puffed up and moving in all directions. Some galaxies were beginning to settle into orderly rotation, but the majority were still turbulent with star formation and gravitational instabilities, stirring up so much disorder that they could barely hold themselves together. This is very different from the neat, orderly picture that some earlier studies had suggested. A few high-profile detections of apparently well-organized massive disk galaxies in the early universe had led some astronomers to conclude that the cosmos settled down faster than models predicted. But the new, more comprehensive survey tells a different story. Those early massive disks appear to be the exception, not the rule. Most early galaxies were a mess. And that messiness matters because it tells us something about the physics of galaxy formation. In a turbulent galaxy, gas cannot cool and collapse into stars as efficiently as it can in a calm, settled disk. But turbulence also drives gas into dense knots and filaments, where star formation can happen in sudden, intense bursts. It is a chaotic process, not a smooth one. This bursty, turbulent picture of early galaxy formation might actually help explain some of the puzzles we have been discussing. If star formation in the early universe happened in intense, irregular bursts, rather than in a steady flow, then the galaxies we observe might sometimes look much brighter than their total mass would suggest. We would be catching them in the middle of a fireworks display, rather than a steady glow. But even with this explanation, the basic puzzle remains. The universe got started faster than we expected. Structure formed sooner. Black holes grew larger. Galaxies assembled more quickly. The fog cleared differently than models predicted, and the expansion rate does not quite match what the early universe tells us it should be. All of these pieces are connected, and putting them together is the great challenge of 21st century cosmology. So where does this leave us? It leaves us in a remarkable position. We are living through a period of scientific discovery that will be remembered for centuries. The James Webb Space Telescope has opened a window into the very beginning of cosmic history, and what it has shown us is both thrilling and humbling. Thrilling because we are seeing things that no human eyes have ever seen before. Galaxies that formed when the universe was still a cosmic infant. Black holes that defy our understanding of physics. Stars that might be the descendants of the very first lights to ever shine. Chemical fingerprints from an era so distant that the light carrying them has been traveling since before the Earth, the Sun, or even the Milky Way existed. And humbling, because nearly every major discovery has come with a reminder that our understanding of the universe is incomplete. We thought we knew when the first galaxies formed. We were wrong. We thought we knew how fast black holes could grow. We were wrong. We thought we understood the pace of cosmic reionization. We were wrong about that too. And we thought two different measurements of the expansion rate would eventually agree. They have not. But this is how science works at its best. Not by confirming what we already believe, but by revealing what we do not yet understand. Every puzzle that Webb creates is an opportunity. Every tension is a signpost pointing toward new physics. The scientists working with Webb data know this. That is why they keep looking. That is why they keep pushing the telescope to its limits, pointing it at ever more distant patches of sky collecting photons that have been traveling for 13 billion years. Because somewhere in those photons is the answer to questions we have not yet thought to ask. Let us take a step back now and look at the bigger picture. Not just the individual discoveries, but the framework they fit into. Because when you put all of Webb's findings together, a pattern starts to emerge. And that pattern tells us something profound about the nature of the universe itself. The universe, at its most fundamental level, is a story about gravity and time. Gravity pulls things together. Time gives them the chance to grow. Every galaxy, every star, every planet, every living thing on Earth exists because gravity had enough time to do its work. Pull gas together, compress it, heat it up, ignite fusion, build structure. The standard model of cosmology gives us a timeline for this process. The Big Bang happens. The universe expands and cools. Atoms form. The dark ages begin. Gravity slowly gathers matter into the first dense clumps. Stars ignite. Galaxies assemble. Black holes grow. Structure builds up generation after generation over billions of years. But what Webb is telling us is that this timeline needs to be compressed at the early end. Things happened faster than the standard picture allows. Not impossibly fast, but uncomfortably fast. Fast enough that the models need adjusting. Fast enough that something we are not accounting for must have been at work. One clue to what that something might be comes from the cosmic web itself. The cosmic web is one of the most remarkable structures in all of nature. If you could zoom out far enough to see the universe on the largest scales, you would not see a uniform sea of galaxies. Instead, you would see a vast network of filaments and nodes, like a three-dimensional spider web stretching across the observable universe. Along these filaments, galaxies are strung like beads on a wire. At the nodes where filaments intersect, you find galaxy clusters, the largest gravitationally bound structures that exist. Between the filaments are enormous voids, regions of space that are almost completely empty. These voids can be hundreds of millions of light years across, containing almost no matter at all. The contrast between the dense filaments and the empty voids is striking. The universe is not smooth. It is lumpy, structured, organized on the grandest scales imaginable. This structure was seeded by the tiniest of differences in the early universe. In the cosmic microwave background, the temperature varies by only about 1 part in 100,000 from one spot to another. Those tiny variations represent slight differences in the density of matter in the early universe. Where the density was slightly higher than average, gravity had a slightly stronger grip, and matter was pulled together a little more effectively. Over 13 billion years, those slight density differences grew into the vast cosmic web we see today. The question is whether those initial density differences were exactly what we think they were. Because if they were even slightly different, even a tiny bit more pronounced in certain regions, it could change the entire timeline of structure formation. And this is where things get really interesting, because some of the most advanced cosmological simulations, the ones that try to reproduce the large-scale structure of the universe, from its initial conditions forward, have always had a small problem. They consistently produce universes that form large galaxies a little later than what observations show. The simulated universes take a little longer to get going than the real universe did. This was a known issue even before Webb, but it was not considered a crisis. It was attributed to the limitations of the simulations themselves, which cannot capture every physical process at every scale. But now that Webb has shown us that the mismatch is even larger than we thought, the simulations are under more pressure than ever. One way to fix the simulations would be to change the initial conditions, make the early density fluctuations a little bit stronger in certain places. This would give gravity a head start, allowing it to build galaxies and black holes faster. But changing the initial conditions means changing our understanding of cosmic inflation, the process that created those conditions. And that is not something physicists do lightly. Another way to fix the simulations would be to change the physics of how gas turns into stars. If the conversion of gas to stars was more efficient in the early universe than it is today, then you could get more massive galaxies in less time. Current models assume that only about 1% of the available gas in a galaxy gets converted into stars at any given time. If that number were closer to 10 or 20% in the early universe, it would help explain what Webb is seeing. But a 20-fold increase in star formation efficiency is hard to justify physically. There are well-understood reasons why star formation is inefficient, including the fact that the energy released by newly formed stars tends to heat up and blow away the surrounding gas, shutting down further star formation. This feedback process is robust and well tested. Overcoming it would require something unusual about the conditions in the early universe. And yet, there are reasons to think those conditions might have been unusual. The early universe was much denser than the universe today. Galaxies were closer together. The gas between galaxies was hotter and more pressurized. In this environment, the normal feedback processes that slow down star formation might not have worked as effectively. Gas that was blown out of a galaxy by a supernova might not have traveled very far before being pulled back in by the galaxy's gravity. The cycle of star formation, explosion, and recollapse might have been faster and more intense than it is today. This is the bursty star formation model we mentioned earlier, and it is one of the most promising explanations for what Webb is seeing. But it is still a hypothesis. It has not been confirmed. And even if it is correct, it only explains part of the puzzle. Because the black holes remain a problem. You can make galaxies brighter by making star formation burstier. But you cannot make black holes heavier by doing that. The black holes need their own explanation. And the heavy seed hypothesis, while compelling, has its own difficulties. For a massive gas cloud to collapse directly into a black hole without fragmenting into stars, first, very specific conditions need to be met. The gas must be metal-free, meaning it has never been enriched by previous generations of stars. It must be illuminated by a nearby source of ultraviolet radiation that can destroy molecular hydrogen, which would otherwise allow the gas to cool and fragment. And the cloud must be massive enough and dense enough to undergo rapid gravitational collapse. These conditions are restrictive. They should be rare. And yet Webb is finding supermassive black holes all over the early universe, not in a handful of galaxies, but in hundreds. The abundance is much higher than the heavy seed scenario predicts. This has led some theorists to explore alternative pathways. Maybe black holes in the early universe could grow faster than the Eddington limit allows. Maybe the Eddington limit, which is based on the balance between gravity and radiation pressure for spherically symmetric accretion, does not apply in the chaotic turbulent conditions of the early cosmos. If gas is flowing into a black hole from multiple directions in streams, rather than a smooth spherical shell, the radiation might escape through gaps in the inflow, allowing the black hole to keep feeding at rates that would otherwise be impossible. This super Eddington accretion has been proposed before, but Webb has given it new urgency. The black hole ELID 568, feeding at 40 times its Eddington limit, is a dramatic example. If this kind of feeding frenzy was common in the early universe, it could explain how black holes grew so large so quickly. And recent simulations from Maynooth University in Ireland have shown that even small black holes, the remnants of the first stars, can grow spectacularly fast in the turbulent conditions of the early cosmos. Their simulations found that the chaotic environment of the early universe, with dense gas flowing in from all directions, provided exactly the conditions needed for light-sea black holes to undergo rapid growth. These tiny black holes, perhaps only 10 to 100 times the mass of the Sun, could reach tens of thousands of solar masses in a remarkably short time. If confirmed, this would mean that we do not need exotic heavy seeds to explain the supermassive black holes in the early universe. We just need the conditions that the early universe apparently provided: dense gas turbulent flows and a galaxy-building process that was far more violent and intense than anything we see in the calm, settled universe of today. This brings us to a deeper question, one that connects all of these individual puzzles into a single narrative. Was the early universe fundamentally different from the universe we live in today? Not just younger, not just smaller, not just less structured, but genuinely different in the way its physics operated? In one sense, the answer is obviously yes. The early universe was denser, hotter, and more chaotic. The laws of physics were the same, but the conditions were extreme enough that certain processes operated differently. Star formation was more intense. Black hole growth was faster. Reionization was more complex. The universe was doing everything at a breakneck pace, as though it were in a hurry to become the structured, organized cosmos we see today. But in another sense, the question goes deeper. Because some of the puzzles that Webb has raised cannot be solved just by tweaking the conditions. If the Hubble tension is real and the expansion rate really is different from what the standard model predicts, then something about the fundamental ingredients of the universe might be wrong. Maybe dark energy is not constant. Maybe dark matter is not as cold and inert as we assumed. Maybe there was an extra ingredient in the early universe, something that has faded away, since that gave everything a boost. These are not minor adjustments. These are the kinds of changes that could reshape our understanding of the cosmos at the deepest level. And the fact that we are even considering them is a measure of how transformative the Webb telescope has been. Let us now go deeper into the darkness. Not the darkness of space, but the darkness of the unknown. The things that Webb has hinted at, but cannot yet prove. The questions that are still open, still waiting for answers. One of those questions involves the nature of the very first structures that formed in the universe. Not the first stars, not the first galaxies, but the dark matter halos that preceded them. In the standard picture, dark matter began clumping together very early, within the first few million years after the Big Bang. These clumps, called dark matter halos, grew over time through mergers and accretion. The first halos were tiny, perhaps containing only a few 100,000 times the mass of the Sun. But they were the gravitational cradles in which the first stars would eventually form. As the halos grew, they pulled in regular matter, the hydrogen and helium gas that would become the raw material for stars. The gas settled into the center of the halos, where it could cool and compress, until conditions were right for star formation. But here is a puzzle that has been around for decades, and that Webb has brought back into sharp focus. We do not know exactly how the first stars formed inside these halos. The process of star formation requires the gas to lose energy to radiate away its heat, so that it can compress further. In the modern universe, heavy elements like carbon and oxygen are excellent at radiating away heat. They act like cooling agents, allowing gas clouds to collapse efficiently. But in the earliest dark matter, halos before any stars had formed, there were no heavy elements. The only cooling agents available were hydrogen molecules, which are much less efficient at radiating heat than heavier elements. This means the gas in the first halos could not cool as effectively, which means it could not compress as much, which means the first stars should have been very different from the ones we see today. Theory predicts that the reduced cooling efficiency would have led to larger, more massive gas clouds collapsing into single stars or small groups of stars. This is why population 3 stars are expected to have been so enormous, hundreds or thousands of times the mass of the Sun. Without efficient cooling, the gas could not fragment into the smaller pieces that would form less massive stars. But exactly how massive these first stars were, how many of them formed in each halo, and how long they lasted, are all still open questions. Different simulations give different answers, depending on the assumptions they make about the physics of gas-cooling magnetic fields, turbulence, and dark matter behavior. Webb cannot directly see population 3 stars. They existed too long ago and died too quickly. But Webb can see. Their indirect effects, the chemical signatures they left behind, the galaxies they helped create, and the black holes they seeded. By studying these indirect effects across hundreds or thousands of early galaxies, scientists hope to build a statistical picture of what the first stars were really like. And the picture that is emerging is already surprising. The chemical signatures found in galaxies like GS-3073 and LP1b suggest that at least some population 3 stars were truly supermassive, with masses between 1,000 and 10,000 times that of the Sun. These are far larger than most simulations had predicted. If such stars were common, they would have had a dramatic impact on the early universe, flooding their surroundings with ultraviolet radiation producing enormous quantities of heavy elements when they exploded and potentially collapsing directly into massive black holes. This brings us full circle. Because the same first stars that ended the cosmic dark ages may also have been the seeds of the supermassive black holes that Webb is finding in such unexpected abundance. The cycle connects. Dark matter pulls gas together. Gas forms enormous stars. Enormous stars live fast and die hard. Their remnants become black holes. The black holes grow rapidly in the chaotic early universe, and the galaxies assemble around them. It is an elegant picture, but it is also one that we are still testing. And the testing will continue for years as Webb accumulates more data and new telescopes come online to complement its observations. One of those upcoming instruments is the Hydrogen Epoch of Reionization Array, or HERA, a radio telescope designed to detect the signal of neutral hydrogen from the epoch of reionization. While Webb sees the light from galaxies, HERA listens for the whisper of the hydrogen gas itself, using a frequency called the 21 centimeter line that is emitted by neutral hydrogen atoms. By mapping this signal across the sky and across different time periods, HERA could give us a three-dimensional picture of how reionization actually happened. Where did the ionized bubbles form first? How quickly did they grow? Did they merge smoothly or in fits and starts? All of these questions would help us understand the discrepancy between the abundance of galaxies that Webb sees and the pace of reionization that other observations suggest. Another important upcoming project is the European Space Agency's Euclid telescope, which launched in 2023 and is mapping the distribution of dark matter across the sky. By comparing the large-scale structure of the universe at different epochs, Euclid can help determine whether the growth of structure has been consistent with the standard model, or whether something extra was at work in the early universe. And then there is the Dark Energy Spectroscopic Instrument, or DESI, which is already producing results. DESI measures the distances to millions of galaxies by studying their spectra, and it uses a pattern called baryon acoustic oscillations as a cosmic ruler to measure the expansion rate of the universe at different times. Early results from DESI largely agree with the standard model prediction for the expansion rate, but there are hints still tentative that dark energy might not be constant after all. If dark energy has been changing over time, that could have profound implications for everything from the expansion rate to the formation of the first structures. All of these instruments, working together, are painting a picture of the universe that is more detailed and more complex than anything we have had before. And at the center of that picture, driving many of the most important questions, is the James Webb Space Telescope. There is one more thread we should follow before we step back and look at the larger picture. It connects the most distant galaxies that Webb has found to the galaxy we live in right now, our own Milky Way. The Milky Way is a large spiral galaxy roughly 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars. It has a supermassive black hole at its center, a bar-shaped structure running through its core and sweeping spiral arms, where new stars are still forming today. It is by any measure an impressive structure. But it was not always this way. 13 billion years ago, the Milky Way did not exist. Not as a recognizable galaxy anyway. What existed instead were the raw ingredients clouds of gas clumps of dark matter, and perhaps a few small irregular proto-galaxies that would eventually merge and grow into the galaxy we call home. The Webb telescope cannot directly observe the infant Milky Way. Our galaxy is here around us, and we cannot see it as it was in the past. But by studying other galaxies at very high redshifts galaxies that existed at the same time and under the same conditions as the Milky Way's ancestors, Webb can tell us what those ancestors probably looked like. And based on what Webb is showing us, the picture is not what we expected. The ancestors of the Milky Way were probably not the tiny, quiet, well-behaved objects that our simulations predicted. They were more likely chaotic, turbulent, and surprisingly active. Some of them may have already harbored black holes that were disproportionately large for their size. Some may have gone through intense bursts of star formation that lit them up like beacons before fading back into relative quiet. The mergers that built the Milky Way would have been messy affairs. Two small galaxies crashing together, their gas clouds colliding and compressing, triggering waves of new star formation. Their central black holes spiraling toward each other, eventually merging in events that would have sent ripples through the fabric of space-time itself. Gravitational waves from those ancient mergers might still be detectable today, spreading outward at the speed of light, carrying information about events that happened more than 12 billion years ago. The European Space Agency's LISA mission, a space-based gravitational wave detector planned for the 2030s, may be able to detect these ancient merger signals. If it does, it would provide a completely independent way to study the same epoch that Webb is observing with light. Gravitational waves and electromagnetic radiation together would give us a stereo view of the early universe, like seeing with two eyes instead of one. This convergence of different observational methods is part of what makes this era of astronomy so exciting. Webb sees the light. Hera will listen for the hydrogen. LISA will feel the gravitational waves. Darcy and Euclid are mapping the large-scale structure. Each instrument sees a different aspect of the same reality, and together they are building a picture that is richer and more detailed than any single telescope could provide. But there is something else about the Milky Way connection that is worth dwelling on. The heavy elements that were forged in the first generations of stars did not stay in the galaxies where they were created. When those early stars exploded as supernovae, they flung material out into intergalactic space. Some of it was captured by neighboring galaxies. Some of it drifted for millions of years before being pulled into new star-forming regions. The universe, even in its earliest epochs, was sharing material across vast distances. This means that the atoms in our solar system, the ones that make up the Earth and everything on it, may have come from many different galaxies, not just from one ancestral proto-galaxy, but from a whole collection of them. The iron in the Earth's core might have been forged in a different proto-galaxy than the carbon in your DNA. The oxygen in our atmosphere might have originated in a star that exploded in a galaxy that later merged with one of the Milky Way's ancestors. We are in a very real sense made from the combined output of many different ancient galaxies. The merger history that built the Milky Way also mixed together the chemical legacies of dozens or hundreds of smaller systems, each one contributing its own batch of heavy elements to the cosmic recipe. This is a humbling thought. We tend to think of ourselves as belonging to one galaxy, one solar system, one planet. But our atoms have a much more complicated history than that. They have been inside stars that no longer exist in galaxies, that no longer have separate identities scattered across regions of space, that are now unrecognizably different from what they were billions of years ago. The Webb telescope, by showing us what those early galaxies looked like, is showing us the places where our atoms were born. Not our specific atoms, of course. We cannot trace individual atoms back to their origin, but the types of galaxies, the types of stars, the types of explosions that produce the elements we are made of. Webb is revealing the cosmic factories that manufactured the raw materials of life. And those factories were running at full capacity far earlier than we expected. Consider what this means for the timeline of heavy element production in the universe. If massive galaxies with elevated levels of nitrogen, carbon, and other elements existed within the first billion years, then the conditions for rocky planet formation and potentially for the chemistry of life were established much earlier than standard models predicted. Rocky planets require heavy elements. You need silicon, iron, magnesium, and oxygen to build a rocky world. You need carbon and nitrogen for organic chemistry. You need water, which requires hydrogen and oxygen. All of these ingredients were being produced in abundance within the first billion years. This does not mean that life appeared that early. There are many steps between having the right elements and having a living organism. But it does mean that the universe was setting the stage for life far sooner than we thought. The clock started ticking earlier. The opportunities were greater. The universe had more time to experiment. And when you consider that the observable universe contains 2 trillion galaxies each with billions of stars, and that the ingredients for life were available across most of cosmic history, the probability that Earth is the only place where life ever appeared starts to look very small indeed. We do not have proof of life elsewhere. That is an important caveat. But the Webb telescope is showing us that the universe is more hospitable, and has been hospitable for longer than we previously understood. The conditions for complexity were established early and spread widely. Whatever life needs to get started, the universe has been providing those ingredients for a very, very long time. Let us now think about what all of this means in a broader sense. Not just for science, but for our understanding of our place in the universe. When you look at a deep field image from the Webb telescope, you are seeing thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. Each of those galaxies contains billions of stars. Many of those stars have planets. The numbers are staggering almost beyond comprehension. And many of those galaxies existed when the universe was still in its infancy. They are not the faint primitive objects we expected. They are vibrant, active, complex. They contain the seeds of everything that would come later, including ultimately us. The heavy elements that were forged in the first stars and scattered by the first supernovae eventually found their way into new generations of stars and planets. Carbon from those ancient explosions is in every cell of your body. Iron from a supernova that happened more than 10 billion years ago is in the hemoglobin in your blood. Oxygen that was cooked up in the core of a star that no longer exists is in the air you are breathing right now. The story that Webb is uncovering is in a very real sense our story. The story of how the universe went from a dark, featureless void to a cosmos filled with light structure and eventually life. We are part of that story. We are made of the same atoms that were forged in those first violent centuries after the Big Bang. We are quite literally the universe looking back at itself, trying to understand how it all began. And what we are learning is that the beginning was more dramatic, more violent, and more mysterious than we ever imagined. Think about this for a moment. The light that the Webb telescope is collecting right now left its source more than 13 billion years ago. When that light began its journey, there were no galaxies like the Milky Way. There was no sun. There was no Earth. There was nothing in the universe that we would recognize. Just gas-dark matter and the faintest beginnings of structure. For 13 billion years, that light traveled through expanding space, its wavelength stretching from ultraviolet to infrared, passing through voids and past galaxies that had not existed when it set out. It survived the expansion of the universe, the formation and destruction of countless stars, the assembly and collision of galaxies. And then, after all that time, it landed on a gold-coated mirror floating in space, 1.5 million kilometers from a small blue planet orbiting an unremarkable star in a spiral arm of a galaxy that would not exist for billions of years after the light began its journey. That is what makes this moment in science so special. We are receiving messages from the very beginning of time, and those messages are telling us things we did not expect to hear. The universe did not wake up slowly from its dark ages. It burst into activity with a fury that our models did not predict. Galaxies formed bigger and faster. Black holes grew larger and more ravenous. The cosmic fog cleared in ways we are still trying to understand. And all of it happened in a universe whose expansion rate does not quite match what its own early conditions predict. We are living in the golden age of observational cosmology. Every month brings new data from Webb and other instruments. Every new paper adds another piece to the puzzle. And the picture that is emerging is one of a universe that is more dynamic, more surprising, and more deeply mysterious than we ever knew. The cosmic dark ages were not the end of a story. They were the beginning. And what came after them, that first explosive awakening of light and structure, is still revealing its secrets. There is a concept in astronomy that most people have heard of, but few truly appreciate, and it is central to everything we have been discussing. It is called redshift. And without understanding it, the discoveries of the Webb telescope remain abstract numbers on a page. When you hear a car approaching and then driving away, the sound changes. As it comes towards you, the sound waves are compressed, making the pitch higher. As it moves away, the waves are stretched, making the pitch lower. This is the Doppler effect, and it works with light just as it works with sound. When a galaxy is moving away from us, the light waves it emits are stretched. Shorter wavelengths of light like blue and ultraviolet get stretched toward longer wavelengths like red and infrared. This is why it is called redshift. The farther away a galaxy is, and the faster it is moving away from us, due to the expansion of the universe, the more its light is stretched. But here is the part that most people miss. The light from the most distant galaxies that Webb observes has not just shifted a little. It has been stretched by a factor of 10 or 12 or even 15. That means ultraviolet light that was emitted by young hot stars has been stretched all the way into the infrared by the time it reaches us. This is why Webb was designed to see in infrared. It was built specifically to detect this stretched ancient light. When astronomers say a galaxy has a redshift of 14, they mean its light has been stretched by a factor of about 15. That corresponds to a time when the universe was only about 290 million years old. The light has been traveling for more than 13 billion years to reach us. And during that journey, the expansion of the universe stretched its wavelength by a factor of 15. This is not just a curiosity. It is the fundamental tool that allows us to use the Webb telescope as a time machine. By looking at increasingly redshifted light, we are looking at increasingly distant objects, and because light travels at a finite speed, increasingly ancient ones. Every increase in redshift takes us further back in time, closer to the Big Bang, closer to the moment when the very first light appeared in the universe. Before Webb, the record for the most distant galaxy was at a redshift of about 11, detected by the Hubble Space Telescope. Webb smashed that record almost immediately, pushing the frontier to redshift 14 and beyond. And at these extreme redshifts, the galaxies are not just faint. They are profoundly different from anything we see in the nearby universe. They are smaller, denser, more active, and chemically simpler. They are windows into a completely different era of cosmic history. But detecting these galaxies is only the first step. To truly understand them, scientists need to do something called spectroscopy, which means splitting the light into its component wavelengths and studying the resulting spectrum. This is enormously more challenging than simply taking a picture because it requires collecting enough photons from each galaxy to create a detailed spectral fingerprint. For the most distant galaxies, this can take tens of hours of telescope time. The JD survey, which has produced many of Webb's most important discoveries, dedicated 75 hours of spectroscopic observation to a single field of sky. That is 3 full days of uninterrupted data collection focused on an area of the sky that you could cover with the tip of your finger held at arm's length. But the results have been worth every second. Spectroscopy has confirmed the distances of the most distant galaxies. It has revealed their chemical compositions. It has measured the velocities of gas within them. It has identified the presence of black holes. And it has provided the data needed to test our models of the early universe against reality. One of the most powerful tools that Webb uses in conjunction with its own observations is gravitational lensing. This is a phenomenon predicted by Albert Einstein's general theory of relativity, which says that massive objects bend the fabric of space-time. When light from a very distant galaxy passes near a massive foreground object like a galaxy cluster, the gravity of that cluster bends and magnifies the distant light, acting like a natural cosmic magnifying glass. The magnification can be enormous. In some cases, gravitational lensing amplifies the light from a background galaxy by a factor of 10 or more. This allows Webb to see galaxies that would otherwise be far too faint to detect, even with its extraordinary sensitivity. The detection of LAP-1b, the galaxy that appears to host population 3 stars, was only possible because of gravitational lensing from the massive galaxy cluster MAX J4 Forms 1sin, which is located about 4.3 billion light-years from Earth. The cluster bent and magnified the light from LAP-1b, which lies more than 13 billion light-years away, making it bright enough for Webb to study in detail. Without gravitational lensing, even Webb's incredible sensitivity would not have been enough to detect objects this faint. Nature itself is providing the extra boost that our technology needs to see the faintest, most distant objects in the cosmos. And the discoveries made possible by gravitational lensing are not limited to population 3 stars. Some of the most distant black holes, some of the most chemically primitive galaxies, and some of the most unexpected structures in the early universe have all been found using this technique. It is as though the universe itself has placed magnifying glasses at convenient locations throughout space, helping us peer ever deeper into its past. There is a beautiful irony in this. The same gravitational force that pulled matter together to form the first stars and galaxies is also the force that bends their light toward us, allowing us to see them. Gravity built the structures, and gravity reveals them to us. It is the architect and the tour guide of the cosmos. Now let us consider something that might seem like a tangent, but is actually deeply connected to everything we have been discussing. It is the question of cosmic noon. Cosmic noon is the period in the universe's history when star formation was at its peak. It occurred roughly 2 to 3 billion years after the Big Bang, corresponding to redshifts between about 1 and 3. During cosmic noon, galaxies were forming stars at rates many times higher than they do today. The universe was a frenzy of activity, with galaxies merging, colliding, and building up their stellar mass at a furious pace. By the time of cosmic noon, the universe had already been through the Dark Ages, the era of the first stars, the epoch of reionization, and the initial assembly of the first galaxies. The small, chaotic, turbulent galaxies of the earliest epoch had already begun to merge and grow into larger, more organized structures, but they were still far more active and energetic than the settled, mature galaxies we see around us today. Cosmic noon is important because it provides a kind of bridge between the very early universe that Webb is revealing and the present-day universe that we observe with other telescopes. By studying galaxies at cosmic noon and comparing them to the earliest galaxies that Webb detects, scientists can trace the evolution of cosmic structure across billions of years. And what they are finding is that the transition from the earliest galaxies to the cosmic noon galaxies was not as smooth and gradual as expected. The earliest galaxies seem to have formed too quickly and too massively for the standard growth curve. If you plot galaxy mass against time, there is a kink in the curve at the earliest epochs. Things were growing faster than they should have been at the very beginning, and then they settled down to a more normal pace by cosmic noon. This kink is one of the most important clues to what was different about the early universe. It suggests that whatever mechanism was accelerating structure formation was most effective in the first few 100 million years, and then faded as the universe expanded and cooled. This is consistent with several of the explanations we have discussed, including bursty star formation, super Eddington black hole growth, and potentially modified initial conditions. It is also consistent with the early dark energy hypothesis. If there was a brief period of extra energy injection in the first few 100,000 years of the universe, it would change the initial conditions for structure formation and potentially produce more massive structures at early times. The effect would be strongest at the earliest epochs and would gradually diminish as the universe aged, which matches the pattern that observations suggest. But early dark energy is just one of many proposals, and it has its own problems. It is difficult to construct a physical model that produces just the right amount of extra energy at just the right time, and then disappears without a trace. Most models of early dark energy either produce too much energy, which would change other observations that we know are correct, or too little, which would not solve the problem. Finding the sweet spot is an ongoing challenge. Meanwhile, other observations are adding new dimensions to the puzzle. The Dark Energy Spectroscopic Instrument DESI has been mapping the distribution of galaxies across a large fraction of the sky, measuring the pattern of baryon acoustic oscillations at different epochs. These oscillations are the remnants of sound waves that traveled through the early universe before the cosmic microwave background was released. They left a characteristic imprint on the distribution of galaxies, like ripples frozen in a pond. By measuring the size of these ripples at different times, DESI can track how the universe has expanded. And while the results largely agree with the standard model, there are hints that dark energy might be more complex than a simple cosmological constant. If dark energy is changing over time, becoming stronger or weaker, it could affect both the expansion rate and the growth of structure in ways that might help resolve some of the tensions. These are early results, and they need to be confirmed with more data. But the fact that multiple independent observations are all pointing to potential problems with the standard model is significant. It is not just Webb. It is not just the Hubble tension. It is a convergence of evidence from different directions that suggests something is off, and that something could be the most important discovery in physics in decades. Let us now return to the darkness. Not the cosmic dark ages this time, but a different kind of darkness. The darkness of what we do not know. We know that the universe is made of about 5% ordinary matter, the stuff we can see, touch and measure. Stars, planets, gas dust, you and me. This is the matter that makes up the periodic table, the atoms that form everything we interact with. We know that about 27% of the universe is dark matter. We have never detected a dark matter particle directly. We do not know what it is made of. We only know it is there because of the gravitational effects it has on things we can see. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters weigh more than their visible contents can account for. The cosmic microwave background has a pattern that only makes sense if dark matter exists. And the cosmic web itself, that vast network of filaments and voids, is shaped by dark matter's gravitational pull. We know that about 68% of the universe is dark energy. This is even more mysterious than dark matter. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. We discovered it in 1998 when two independent teams measured the brightness of distant supernovae and found that the expansion was speeding up rather than slowing down. One of those teams was led by Adam Rees, the same scientist who is now at the center of the Hubble tension story. Dark energy behaves like a kind of anti-gravity. While gravity pulls matter together, dark energy pushes space apart. And it is winning. The expansion of the universe is accelerating, which means that the distances between galaxies are growing faster and faster over time. But we do not know what dark energy is. The simplest explanation is Einstein's cosmological constant, a fixed amount of energy inherent to empty space. But other models propose that dark energy is a dynamic field that changes over time, sometimes called quintessence. If dark energy is dynamic, it could have been different in the early universe, which would change the timeline of cosmic evolution. Webb's observations of the early universe are indirectly probing the nature of dark energy. By studying when and how the first structures formed, scientists can place constraints on how much dark energy was present at different times. If dark energy was stronger in the early universe, it would have affected the growth of structure. If it was weaker, structure would have grown more easily. The balance between gravity pulling things together and dark energy pushing them apart determines the entire history of cosmic evolution. And right now, the balance does not seem to quite work out. The early universe formed more structure than we expected. The current universe is expanding faster than the early universe predicts. Dark energy might be the link between these two puzzles, but proving it will require much more data and probably new physics. This is the frontier of human knowledge. This is where the known ends and the unknown begins. And the Webb telescope is standing right at that border, shining its golden mirror into the darkness and sending back images of things we have never seen before. Let me tell you about one more discovery because it captures the spirit of what makes this era of astronomy so exciting. In the early months of Webb's operations, astronomers noticed something peculiar in the deep field images. Among the thousands of galaxies scattered across the field, there were tiny, compact red objects that did not quite fit into any known category. They were too red to be normal galaxies. They were too compact to be regular star-forming systems. And they were found in enormous numbers, far more than anyone had predicted. Scientists initially called them little red dots, a deliberately vague name chosen, because nobody was quite sure what they were. As more data came in, the picture became more complex. Some of the little red dots appeared to be compact galaxies with very active central black holes. The black holes were heating up surrounding gas and producing the red glow that made these objects stand out. Others appeared to be dusty star-forming galaxies, where the dust was absorbing shorter wavelengths of light and re-emitting them in the red and infrared. But many of the little red dots defied simple classification. They showed spectral features that were inconsistent with either a pure black hole or a pure star-forming galaxy. They seemed to be some kind of hybrid, a transitional object that exists in the boundary between the two. The discovery of these objects was not just a scientific curiosity. It had practical implications for other studies. When astronomers estimated the masses of early galaxies based on their brightness, the little red dots were often included in the analysis. If a little red dot is actually a compact galaxy with an overactive black hole, then its true stellar mass is much lower than its brightness would suggest. Removing the little red dots from the galaxy census changed the picture, significantly reducing the number of genuinely massive early galaxies and easing some of the tension with the standard model. But even after removing the little red dots, there were still more massive galaxies in the early universe than expected. The puzzle did not go away entirely. It just became a bit less extreme. And the little red dots themselves remain fascinating objects. They appear to be 10 to 100 times more common in the early universe than similar objects are today. Whatever they are, they were a significant part of the cosmic landscape at very early times and have largely disappeared since. Understanding what they are, how they formed, and why they are so abundant is a major ongoing research effort. Some scientists think the little red dots might be the missing link between the first seed black holes and the supermassive black holes we see in modern galaxies. If these objects represent a phase in which small black holes are rapidly growing by consuming gas, then they would naturally be more common at early times when gas was plentiful and conditions were right for rapid growth. As the universe aged and gas became scarcer, these objects would fade away, leaving behind the mature supermassive black holes that sit quietly at the centers of modern galaxies. If this picture is correct, then the little red dots are not mysterious anomalies. They are snapshots of a crucial phase in the life cycle of black holes and galaxies, a phase that we have never been able to observe before because it happened so long ago and was invisible to earlier telescopes. Webb has opened the window on this hidden chapter of cosmic history, and that is really the theme that runs through all of these discoveries. Hidden chapters, things that were there all along but that we could not see. The early universe was not the simple empty place we imagined. It was rich, complex, active, and full of objects and processes that we are only now beginning to understand. The cosmic dark ages were not truly dark. They were a period of intense gravitational activity as dark matter pulled together the scaffolding on which everything else would be built. The epoch of reionization was not a smooth, predictable process. It was messy, complicated, and driven by a galaxy population that was more abundant and more energetic than anyone expected. The first galaxies were not the tiny, feeble things our models predicted. They were big, bright, and surprisingly mature. The first black holes were not small seeds waiting patiently to grow. They were voracious monsters that devoured their surroundings at impossible rates. And the universe itself, the fabric of space-time in which all of this unfolds, may not be expanding in quite the way we thought it was. Every one of these findings is a challenge to our understanding. Every one of them is an invitation to think deeper, to question our assumptions, to push the boundaries of what we know. And every one of them has come from a single instrument floating in the cold darkness of space, collecting photons that have been traveling since the universe was barely a whisper of what it would become. The Webb telescope has been operating for just a few years. It is expected to continue for decades. The discoveries made so far are extraordinary, but they are just the beginning. Future observations will push to even higher redshifts, even more distant and ancient objects. New surveys will map the early universe in unprecedented detail. and new generations of scientists will use the data to develop new theories, test new models, and perhaps discover new physics. We do not know what the universe will reveal next. That is what makes this so exciting. We are explorers standing on the shore of an unknown ocean with a telescope powerful enough to see to the other side. And what we are seeing is changing everything. There is a thought experiment that astronomers sometimes use to put these discoveries in perspective. Imagine you could somehow compress the entire 13.8 billion year history of the universe into a single year. The Big Bang happens at midnight on January 1st. Under this timescale, the cosmic dark ages last through most of January. The first stars ignite sometime around January 10th. The first galaxies appear later that month. Our Milky Way starts forming sometime in March or April. The Sun and Earth do not appear until September. The dinosaurs go extinct on December 26th. All of recorded human history takes place in the last few seconds before midnight on December 31st. The period that the Webb telescope is studying, the first few 100 million years after the Big Bang, corresponds to roughly the first 10 days of January in this compressed calendar. And in those 10 days, the universe went from a formless dark void to a cosmos populated by billions of stars organized into galaxies, illuminated by the light of the first suns, and already building the supermassive black holes that would anchor the largest structures in the universe. 10 days out of a full year. That is how compressed the action was at the beginning. The universe did not ease into existence. It erupted. And the thing that makes this so hard to explain is not that structure formed. We expected that. It is that structure formed so quickly and so prolifically that our best models cannot account for it without significant adjustments. Let me put it another way. Imagine you plant a seed in a garden. You know, based on everything you understand about plant biology, that the seed should take 6 months to grow into a full-sized tree. But when you come back 3 weeks later, the tree is already there. Fully grown branches reaching up to the sky, leaves catching the sunlight. The seed became a tree which you expected. But it became a tree much faster than your understanding of plant biology says it should have. That is essentially what happened with the early universe. The galaxies grew, the black holes formed, the stars ignited, all of which was expected. But it all happened faster and on a larger scale than our models predicted. The tree was already there when we looked, and we are still trying to figure out how it grew so fast. This is why the Webb telescope is not just another astronomical instrument. It is a tool for testing the fundamental laws of physics. Every time it observes a distant galaxy that is more massive than expected, or a black hole that is larger than it should be, or a chemical signature that does not fit the standard timeline, it is probing the limits of our understanding, not just of astronomy but of physics itself. And the implications extend far beyond the early universe. If the standard model of cosmology needs to be revised, the changes will ripple through every branch of physics. A new form of dark energy would affect particle physics. A new type of dark matter interaction would affect our understanding of the fundamental forces. A modification to the theory of inflation would affect our ideas about the very first instant of creation. These connections are part of what makes cosmology so powerful. The universe is the ultimate laboratory. It has already run every experiment at every energy scale across every time period. We just need to figure out how to read the results. And the Webb telescope is giving us the clearest reading we have ever had. There is another aspect of these discoveries that deserves attention, because it often gets overlooked in the excitement about distant galaxies and ancient black holes. It is the sheer improbability of the universe producing observers capable of understanding it. Think about the chain of events that connects the cosmic dark ages to this conversation. Hydrogen atoms formed in the cooling aftermath of the Big Bang. Those atoms gathered into clouds under the pull of dark matter. The clouds collapsed into the first stars. Those stars burned through their fuel and exploded, scattering heavy elements into space. New stars formed from the enriched gas, some with planets around them. On at least one of those planets, the conditions were right for complex chemistry, for self-replicating molecules for life. Over billions of years, life evolved from simple cells to complex organisms, eventually producing beings capable of abstract thought mathematics and the construction of telescopes. Those beings pointed their telescopes at the sky and detected the light from the very same process that created them, light from the first stars, from the first galaxies, from the very beginning of the chain of events that led to their existence. There is something deeply circular about this. The universe created the conditions for life. Life evolved the capacity to observe the universe, and the observations reveal the process by which life was made possible. We are the universe's way of looking back at its own birth. This is not a mystical statement. It is a factual description of the situation. The atoms in the Webb telescope's mirror were forged in ancient stars. The gold that coats those mirrors was created in neutron star collisions or supernovae billions of years ago. The silicon in the telescope's electronics came from stellar nucleosynthesis. Even the knowledge that allows us to build such an instrument is encoded in brains made of atoms that were assembled in the hearts of stars. Everything connects back to the beginning, and the Webb telescope, by showing us that beginning in unprecedented detail, is completing the circle. Let us go deeper still. Let us think about what these discoveries might mean for questions that science alone cannot fully answer. The existence of structure in the early universe, the emergence of complexity from simplicity, the fine-tuned balance between gravity and expansion that allows anything to exist at all. These are facts that can be described by physics, but that also raise questions about the nature of reality itself. Why does the universe have the properties that allow structure to form? Why are the fundamental constants, the strength of gravity, the masses of particles, the energy of dark energy, tuned in such a way that stars can form, that heavy elements can be created, that life can emerge? If gravity was slightly stronger, the universe would have collapsed back on itself before any stars could form. If gravity was slightly weaker, matter would never have clumped together at all, and the universe would be a thin, featureless gas, forever expanding into nothing. If the strong nuclear force were slightly different, hydrogen could not fuse into helium, and stars would not shine. If the electromagnetic force were slightly different, atoms would not hold together, and chemistry would be impossible. The universe appears to be balanced on a knife's edge, and the discoveries that Webb is making push that knife's edge even further into view. The early universe managed to produce an enormous amount of structure in a very short time, as though the initial conditions were optimized for rapid growth. Was this inevitable? Was it designed? Was it just one outcome among an infinite number of possibilities? These are questions that physics cannot answer definitively. They are questions that border on philosophy, on metaphysics, on the fundamental mystery of existence. But they are questions that are brought into sharper focus by every discovery that Webb makes. The more we learn about the early universe, the more remarkable it appears. Not just because of what happened, but because of the precision with which it happened. The fact that the initial density fluctuations were just the right size, the fact that the expansion rate was just the right speed, the fact that the fundamental forces were just the right strength, all of these things conspired to produce a universe that went from featureless soup to organized structure in a remarkably short time. And now, billions of years later, the descendants of those first stars are pointing a golden mirror at the sky and trying to figure out how it all worked. Let us come back to the specifics one more time, because the science itself is endlessly fascinating. One of the things that Webb has revealed about the early universe is that galaxy formation was not a one-size-fits-all process. Different galaxies followed different paths. Some assembled quickly through rapid bursts of star formation. Others grew slowly through the gradual accumulation of gas. Some were dominated by their central black holes, which shaped the galaxy's evolution through their powerful outflows of energy. Others were dominated by stars, with the black hole playing a secondary role. This diversity is itself a surprise. In the simplest models of galaxy formation, the early universe should have produced a fairly uniform population of small, simple galaxies. But Webb has shown that the earliest galaxies were already diverse, with a range of sizes, shapes, chemical compositions, and star formation histories. The cosmos was already experimenting with different ways of building structure, even when it was less than 1 billion years old. This diversity has practical implications for how we study the early universe. You cannot treat all early galaxies as interchangeable. Each one is an individual with its own history, its own chemical fingerprint, its own relationship between stars and black hole. To understand the population as a whole, you need large samples, comprehensive surveys, and detailed spectroscopic follow-up. This is why programs like JD's are so important. They provide the large, well-characterized samples that are needed to draw meaningful statistical conclusions. And the conclusions that are emerging from these surveys are reshaping our understanding of cosmic history. Let us also consider the implications for the search for life beyond Earth. One of the most profound questions in all of science is whether we are alone in the universe. The answer depends in part on how quickly the conditions for life were established. The Webb telescope's discoveries tell us that heavy elements, the building blocks of rocky planets and the chemistry of life, were being produced in significant quantities within the first billion years of cosmic history. Galaxies like GS-30U73 already contained elevated levels of nitrogen and other elements just 1 billion years after the Big Bang. This means that the raw materials for planet formation and potentially for life were available much earlier than previously assumed. If planets could form around second or third generation stars within the first 1 to 2 billion years of cosmic history, and if those planets could develop the conditions necessary for life, then life might have a much longer history in the universe than we previously thought. There could be civilizations out there that are billions of years older than ours. Or there could be planets that once harbored life but have long since gone dark. The timeline of possibility is much longer than we realized. This is speculation, of course. We have no evidence for life beyond Earth. But the fact that the chemical ingredients were in place so early in cosmic history expands the window of opportunity enormously. And it adds another layer of significance to what the Webb telescope is finding. Now, as we approach the end of this journey, let us take one last look at the big picture. The James Webb Space Telescope saw the first objects beyond the dark ages. It found galaxies that were bigger and brighter than expected. It found black holes that were more massive and more abundant than predicted. It found chemical signatures that hint at the existence of the first generation of stars. It found a reionization process that was more complex than models suggested. And it confirmed that the expansion rate of the universe does not match what its own early history predicts. Each of these discoveries on its own would be a major milestone. Together, they represent a revolution in our understanding of cosmic history. The early universe was not the quiet, simple place we imagined. it was a cauldron of activity producing structure at a pace that challenges our best theories and forces us to consider the possibility that our understanding of the fundamental laws of nature is incomplete. This is not a crisis in the negative sense. It is a crisis in the scientific sense, a moment when established ideas are confronted with new evidence and forced to evolve. The history of science is full of such moments, and they are almost always followed by periods of rapid progress. The tension between observation and theory is the engine that drives discovery. Right now, that engine is running at full power. Every observation that Webb makes tightens the constraints on what our theories must explain. Every anomaly that it uncovers narrows the range of possible solutions. And somewhere in those solutions waiting to be discovered may be the next great insight into the nature of reality. Will it be a new form of dark energy, a new property of dark matter, a modification to our understanding of gravity, a change to the physics of inflation? Something entirely unexpected that nobody has thought of yet? We do not know. That is the honest answer. And it is in its own way the most exciting answer possible, because it means the story is not over. It means there is more to learn. It means the universe still has secrets to share. And the golden mirror of the Webb telescope is listening. As you lie here, perhaps drifting towards sleep, consider this. Every atom in your body was once part of a gas cloud in the early universe. That gas was gathered by gravity into a star that burned for millions or billions of years and then exploded, scattering its contents across space. Those contents were gathered again into new clouds, new stars, eventually into a planet that orbited a medium-sized star in the spiral arm of an unremarkable galaxy. On that planet, over billions of years, the conditions were right for something remarkable to happen. Simple molecules became complex ones. Chemistry became biology. Biology became consciousness. And consciousness looked up at the sky and wondered where it all came from. The Webb telescope is part of the answer. Not the whole answer. Not even close. But a part. A crucial part. A window into the deep past that is teaching us about the very beginning of the story that eventually led to us. The cosmic dark ages were the prelude. The first light was the opening act. And everything that has happened since, every star, every galaxy, every black hole, every planet, every living thing, is part of the same unfolding story. We are in the middle of that story right now. We do not know how it ends. We do not know all of its chapters. But thanks to the James Webb Space Telescope, we can read the first pages more clearly than ever before. And what we are hearing is beautiful, mysterious, and full of surprises. The universe is bigger than we thought. Older in its complexity, if not in its age. More violent in its youth. More mysterious in its fundamental nature. And more wonderful than any human mind could have invented. Out there in the darkness beyond the dark ages, the first light still shines. It has been shining for more than 13 billion years. It has crossed voids that would take millions of lifetimes to traverse. It has passed through expanding space, its wavelength stretching, its energy fading, but its message intact. And that message carried across the entire history of the universe is this. Something happened here. Something incredible. Something that turned a featureless void into a cosmos of galaxies and stars and planets and life. Something that we are only just beginning to understand. The Webb telescope caught that message. It translated it from infrared photons into images and spectra and data. And from that data, we are piecing together the story of our origins. Not our origins as a species or as a planet, or even as a galaxy. Our origins as a universe. The moment when nothing became something, when dark became light, when silence became the first sound of a cosmos waking up. That is what the James Webb Telescope saw beyond the dark ages. Not just the first objects, not just the first galaxies, but the very first chapter of the story of everything. And the story is far from over. For now, as the telescope continues its silent orbit around the Sun, collecting photons from the edge of time, the universe keeps expanding, keeps cooling, keeps evolving. New stars are being born right now in gas clouds scattered across the Milky Way. New planets are forming around those stars. And somewhere on one of those planets, or on a world we have not yet discovered, life might be beginning the same journey that we began billions of years ago. The chain that connects the cosmic dark ages to this moment is unbroken. It stretches from the first hydrogen atoms to the last thought you will have tonight before sleep. And every link in that chain was forged in the furnace of a universe that was in a hurry to become something extraordinary. If you look up at the sky on a clear night, you will see stars, thousands of them scattered across the vault of the heavens. Each one is a furnace burning hydrogen into helium, just like the very first stars did. Each one is a link in the same chain. And beyond those stars, far beyond in the deepest reaches of space, the Webb telescope is watching the very beginning of that chain, tracing it back to the first moment when light existed, the first moment when the universe was no longer dark. That light is still arriving. It will keep arriving for as long as the telescope keeps looking. And with each photon, we learn a little more about where we came from, what we are made of, and how the universe became the astonishing place that it is. The dark ages ended. The light came, and we were eventually here to see it. That might be the most remarkable thing of all. There is one more piece of this puzzle that we should explore before we let these ideas settle. It is a piece that connects the smallest scales of physics to the largest scales of cosmology, and it has to do with a question that sounds simple, but is actually one of the deepest in all of science. How do you weigh a galaxy? This might seem like a strange question. Galaxies are enormous after all. How could you possibly put one on a scale? But astronomers have figured out multiple ways to estimate the mass of a galaxy, and those methods are at the heart of many of the debates that Webb has sparked. The most straightforward method is to add up all the light a galaxy produces and convert that into an estimate of how many stars it must contain. This is called the luminosity method. If you know how bright a typical star is, and you know the total brightness of the galaxy, you can estimate the total number of stars, and from that, the total stellar mass. But this method has a crucial weakness. It assumes you know what kind of stars are producing the light. If the galaxy is full of young, hot, massive stars, then a given amount of light corresponds to fewer total stars and less total mass. If the galaxy is full of older, cooler, less massive stars, the same amount of light corresponds to more stars and more mass. The mix of star types called the stellar population matters enormously. In the early universe, this problem becomes acute. We do not have a good understanding of what the stellar populations of the earliest galaxies looked like. They might have been dominated by very massive, very bright stars that would make the galaxy appear more luminous than its total mass would suggest. Or they might have already developed a mix of star types that is closer to what we see in modern galaxies. The answer affects everything. A second method involves studying the velocities of gas and stars within the galaxy. If you can measure how fast things are moving, you can use Newton's laws to calculate how much gravitational pull is holding the galaxy together, and from that, how much total mass it must have. This method captures not just the stellar mass, but also the dark matter mass, giving a more complete picture. But this method requires detailed spectroscopic observations that are extremely challenging for the most distant galaxies. The light is faint, the galaxies are small, and the measurements are at the very limit of what even Webb can achieve. A third method involves fitting theoretical models to the observed spectrum of the galaxy. By comparing the galaxy's light to a library of simulated spectra, scientists can estimate properties like the star formation rate, the stellar age, the chemical composition, and the total stellar mass. This method, called spectral energy distribution fitting, is powerful, but depends heavily on the assumptions built into the models. And this is where the trouble begins, because the models were built using our understanding of how stars form and evolve in the nearby universe. If the physics of star formation was different in the early universe, as several lines of evidence now suggest, then the models might be giving us incorrect answers. Some scientists think that the masses of early galaxies have been significantly overestimated, because the models do not account for the different stellar populations and star formation histories that prevailed at that time. Others think the masses are roughly correct, which means the standard model of cosmology really does need some adjustment. This debate is not just an academic exercise. It goes to the heart of what the Webb telescope is telling us. Are the early galaxies really as massive as they appear? Or are we being fooled by unfamiliar conditions? The answer will determine whether the standard model survives intact or needs to be significantly revised. And the answer is probably somewhere in between. The early galaxies are not quite as massive as the most dramatic initial estimates suggested. The little red dots inflated some of the numbers. Bursty star formation makes some galaxies appear brighter than their mass warrants, and our models of stellar populations are being updated to better reflect the conditions of the early cosmos. But even after all of these corrections, the early universe remains more structured, more active, and more productive than the standard model comfortably predicts. The tension has been reduced, but it has not been eliminated, and that persistent tension is the most scientifically valuable outcome of all, because it means there is something left to discover, something about the universe that we have not yet figured out, and that something could be the key to the next great leap in our understanding of reality. Let us also pause to appreciate the human dimension of these discoveries. Behind every data point from the Webb telescope, there is a team of scientists who spent years, sometimes decades, preparing for this moment. The telescope itself was proposed in 1996, nearly 30 years ago. It took 25 years to design, build, test, and launch. Thousands of engineers, scientists, and technicians contributed to its creation. Many of the people who started working on the Webb telescope at the beginning of their careers retired before it launched. Some did not live to see its first images. The telescope is a monument to human patience, ingenuity, and the willingness to invest in a future that you might not be around to see. And the science that it is producing is the work of hundreds of researchers around the world, working in teams that span continents and time zones. The JWST survey alone involves more than 100 scientists from dozens of institutions. The data they collect is analyzed, debated, challenged, revised, and refined in an ongoing process that represents science at its very best. When a new result is published, it is not the end of this story. It is the beginning of a conversation. Other teams check the work, test the conclusions, propose alternative explanations, and design new observations to resolve the disagreements. This process is slow, messy, and sometimes contentious. But it is the reason we can trust the results. Science does not claim to have all the answers. It claims to have the best method for finding them. And right now, that method is pointed at the beginning of time. There is a concept in cosmology called the observable universe. It is the region of space from which light has had time to reach us since the Big Bang. Beyond this boundary, There may be more universe, potentially an infinite amount more, but we cannot see it because its light has not arrived yet. The observable universe has a radius of about 46 billion light years in every direction. That number is larger than the age of the universe in light years because space itself has been expanding while the light was traveling. The most distant light we can detect, the cosmic microwave background, comes from a surface that is now 46 billion light years away, even though the light has been traveling for only 13.8 billion years. Within this observable universe, there are estimated to be 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star may have planets. The numbers are beyond human comprehension. And the Webb telescope, by looking at the most distant reaches of this observable universe, is showing us that the process of building all of this structure began earlier, faster, and more violently than we ever imagined. The cosmic dark ages were not a peaceful slumber. They were the calm before a storm of creation that would eventually produce everything we see around us. The universe did not gently ease into existence. It ignited, and it has been burning ever since. Every galaxy that Webb observes in the deep field is a record of that ignition. Every spectrum it collects is a piece of evidence about how the fire started and how it spread. Every anomaly it discovers is a clue to something we do not yet understand about the nature of the fire itself. We are living in extraordinary times. The tools we have built are powerful enough to see to the edge of the observable universe and back to the beginning of time. The questions we are asking are the most fundamental that science can pose, and the answers we are finding are more surprising, more challenging, and more beautiful than we had any right to expect. The Webb telescope saw the first objects beyond the dark ages. What it found stunned everyone, not because the universe was disappointing, but because it was so much more than we ever dared to imagine. Out there beyond the darkness, the universe was already building something incredible. It was building galaxies from scratch, forging elements in nuclear furnaces, growing black holes in the hearts of young galaxies, and flooding the cosmos with light for the very first time. It was building the foundations of everything that would come later. Every star in the sky tonight, every planet orbiting those stars, every atom in every living thing on every world, all of it started there in those first few 100 million years after the Big Bang, in the fury of a universe that was just getting started. And now, 13 billion years later, we are looking back at that moment. We are studying it with the most powerful instrument humanity has ever built, and we are discovering that the beginning was wilder, stranger, and more mysterious than any of us expected. The story of the universe is the story of us. And thanks to the James Webb Space Telescope, we are reading the first page for the very first time. What will we find on the next page? Nobody knows. But the telescope is turning the page right now, every day, every hour, every minute, collecting photons, building spectra, measuring distances, revealing secrets that have been hidden for 13 billion years. And somewhere in those secrets, there is an answer waiting. An answer to a question we have been asking since the first human looked up at the stars and wondered what they were. How did all of this begin? We are closer to that answer than we have ever been, and the journey is only beginning.